All right, let's jump right into this explainer and completely master the hidden mechanics of two-dimensional motion. Today, we're going to crack the code on how the physical world handles objects moving in two directions at once. We're talking everything from a soaring circus lion to a cyclist taking a sharp turn. If you've ever felt completely intimidated by the physics of flying objects or circular tracks in your exams, don't sweat it. By the end of this, you'll see exactly how elegant, predictable, and honestly scoreable these motions really are. Here is our quick roadmap for the next few minutes. We're covering two-dimensional motion basics, the projectile trajectory, projectile energy and momentum, uniform circular motion, acceleration and forces, and wrapping up with motion in vertical circles. Let's get to it. Section 1. Two-dimensional motion basics, vertical and horizontal independence. Let's start with the absolute fundamentals of motion happening in two planes simultaneously.
Think about a circus lion jumping through a ring of fire. It's not just a cool trick, it is the absolute perfect example of the physical independence of motions. You see, when a body is in flight, its horizontal motion and its vertical motion are completely independent of each other. The lion is moving forward with a constant horizontal speed, right? But gravity is simultaneously pulling him straight down. These two actions, they literally don't care about one another. They don't interfere, they just perfectly combine to create that beautiful, predictable arc.
Okay, before you even think about calculating distances and heights, you've got to know the ground rules. To solve projectile problems without losing your mind, you must first memorize these 4 idealized assumptions. In our physics sandbox, we just pretend air resistance doesn't exist. We ignore the curvature and rotation of the Earth, and we assume gravity is just this constant, unchanging downward force. Without these assumptions, the math becomes an absolute nightmare. So keep these in your back pocket for your exams. Now here is a classic physics scenario that pops up all the time. Imagine a hunter aiming his barrel on a perfectly straight line right at a monkey hanging in a distant tree. But as we know, the bullet is a projectile, right? So it's not going to fly perfectly straight. Gravity's going to bend its path downward the second it leaves the barrel. So here is the ultimate exam trap. If that monkey lets go and drops the exact instant the gun is fired, will the bullet still hit it? Take a second to really think about the independence of vertical and horizontal motion we just talked about. Because gravity pulls both the bullet and the monkey downward at the exact same rate, that bullet falls away from its straight line path by the exact same vertical distance that the monkey falls from the tree. So yes, crazy enough, they will collide in midair every single time. Section 2. The projectile trajectory, mapping the parabola. Moving on, let's look at the actual mathematical path of the projectile. You literally have to know these trajectory formulas for your exams. The top equation looks like an absolute beast, I know, but notice that x squared term. That mathematically proves right there that the path of a projectile is a parabola. But hey, look at the bottom equation. That shortcut form using r for range, that is an absolute lifesaver. When a numerical question gives you the angle and the range, using this shortcut will literally save you valuable minutes on the clock.
And speaking of range, please don't fall for this incredibly common numerical trap. Complementary angles of projection, meaning two angles that add up to 90 degrees, like 30 degrees and 60 degrees, well, they will always give you the exact same horizontal range, assuming your initial speed is the same. One is going to fly much higher, and the other will stay lower and fly faster, but they are going to land on the exact same spot.
Section 3. Projectile energy and momentum, conservation in flight. Let's track how energy behaves during this parabolic flight.
Let's break down energy conservation here, because this is where a lot of points are lost. A super common mistake is thinking kinetic energy just drops to 0 at the highest point of the trajectory. It totally doesn't. While the vertical velocity becomes 0 at the peak, remember that horizontal velocity? It just continues along unchanged. So your kinetic energy reaches a minimum based on the cosine squared of the projection angle, while potential energy hits its absolute max. The total mechanical energy, though, that stays completely constant the whole time. Section 4. Uniform circular motion, from parabolas to circles. All right, let's shift gears from parabolic arcs to objects constrained to a continuous loop. Think of these concepts as your personal translation dictionary. You need to be able to smoothly convert between linear variables, like normal velocity, and angular variables, like angular velocity, which we represent with the Greek letter omega. Now, in uniform circular motion, omega remains perfectly constant. Make sure you really lock in that final relationship. Angular velocity equals 2 pi times frequency. It's the ultimate bridge between how many times something spins and how fast the angle itself is actually changing. Section 5. Acceleration and forces, centripetal versus centrifugal. So, What actually forces an object to constantly change direction and move in a circle instead of just flying off in a straight line? Picture a cyclist leaning hard into a sharp turn. By Newton's laws, if that cyclist's direction is constantly changing, there absolutely must be a net inward force acting on him. In this real-world case, that necessary centripetal or center-seeking force is provided by the friction between the road and the tires. If that friction suddenly disappears, like if he hits a patch of ice, the centripetal force vanishes instantly and our cyclist goes straight off the track. Okay, here is a massive conceptual trap. Don't confuse your forces. We've all been on a spinning amusement park ride and felt like we're being physically pushed outward. But remember, centrifugal force is totally imaginary. It is a fictitious force. It's merely the effect of your body's inertia wanting to go in a straight line while your actual frame of reference is rotating. It is not a real physical push like centripetal force is. Keep that distinction crystal clear.
This is why you really have to read your exam questions carefully. If a particle is just changing direction at a constant speed, it only has centripetal acceleration. Easy enough. But non-uniform circular motion, that is tricky. If the speed is changing while it's turning, it has both tangential acceleration and centripetal acceleration. That means you must calculate a net acceleration vector using the Pythagorean theorem. Don't let them catch you on that.
Section 6. Motion in vertical circles. Non-uniform circular motion. Let's look at the most extreme case of non-uniform circular motion under the influence of gravity, vertical circles. Imagine swinging a bucket of water on a string in a huge vertical circle. As it goes up, gravity fights it and slows it down. As it comes down, gravity speeds it right back up. To safely complete a full vertical loop without the string going completely slack at the very top, the object needs a specific amount of kinetic energy at the bottom. That absolute minimum lowest point velocity, it must equal the square root of 5 times gravity times the radius of the circle. This relationship is incredibly popular in entrance exams, so definitely burn that one into your memory.
And that brings us to the end of our breakdown. Two-dimensional motion governs everything from thrown basketballs to the orbits of planets. It can seem incredibly complex at first glance, but as you've seen today, it all breaks down into independent components, conserved energy, and predictable forces. Mastering these mathematical relationships is your ultimate key to unlocking exam success. Before you go, chew on this thought experiment. If you were standing on a scale inside an elevator that was in free fall and you threw a ball perfectly horizontally, what exact path would that ball take from your perspective? Think about it. Thanks for learning with me in this explainer, and keep that curiosity going.
Welcome to This Explainer. Today, we're going to unpack the hidden physics behind everyday motion, spectacular sports, and those breathtaking stunts you see on screen. Because whether you realize it or not, the world around us is governed by this invisible, completely unbreakable set of rules. And one of the most fascinating sets of rules involves something called projectile motion. If you've ever thrown a ball, jumped over a puddle, or just watched a crazy action movie, you have seen this in action. But today, we are going to truly understand it. Take a look at this absolute death-defying circus stunt. We've got a magnificent lion leaping gracefully through a blazing ring of fire suspended high in the air. It looks like pure instinct and bravery, doesn't it? But beneath all that spectacle, whether they consciously know the exact math or not, the performers are executing absolute perfect physics. In fact, our source text hits the nail on the head here. Surviving this fiery jump requires a flawless grasp of projectile motion. If that lion jumps a fraction too early, a second too late, too high or too flat, the whole stunt ends in total disaster. Mastering that exact leap is precisely what we're going to break down today, using the fundamental principles of physics. Section 1. What is projectile motion? Okay, so in physics, a projectile is literally just any body in flight through the atmosphere that isn't being propelled by fuel. To really wrap our heads around this, let's look at a classic physics mystery from our source material. Imagine a hunter aims a gun directly at a monkey sitting in a distant tree. Now, if the monkey just sits there, the bullet will actually miss, passing right below it. But suppose the monkey gets spooked and drops from the tree at the exact millisecond the gun is fired. Don't worry, no actual monkeys were harmed in this thought experiment, but what do you think happens next? Boom, the bullet hits the monkey. Why? Well, this brilliantly illustrates the reality of projectile motion. Notice how the bullet doesn't travel in some perfectly straight, laser-like line. It actually falls in a curved path because of gravity. So, as the monkey falls, the bullet is falling at the exact same vertical rate.
Because gravity accelerates both the monkey and the bullet downwards equally, their paths perfectly intersect. That right there, that is projectile motion in action.
Section 2. Two independent motions.
So, the absolutely crucial point here is something physicists call the principle of physical independence of motions. I know, it sounds like a mouthful, but it's actually beautifully simple. When an object is flying through the air, it is living in two completely independent realities at the exact same time, a horizontal reality and a vertical reality. Horizontally, the motion is uniform. The speed is totally constant because, assuming no air resistance, nothing is pushing or pulling it side to side. But vertically, gravity is constantly yanking it down, which means the vertical velocity is always changing.
Let's bring this down to earth with a real-world example from the text. Picture a skateboarder jumping over a hurdle while their board rolls underneath them. When they leap, their vertical velocity changes, right? They go up, stop for a fraction of a second at the peak, and then come down. But horizontally, their forward speed stays completely constant, perfectly matching the rolling skateboard below them. And that is exactly why they can land safely back on the board. The vertical jump didn't mess with their horizontal forward momentum at all.
Section 3. Mapping the parabolic path.
When you mash these two independent motions together, you get this beautiful curve known as a parabola. This shape happens specifically because of those two independent realities we just talked about. The object is being pushed forward at a steady, unchanging pace, while simultaneously being pulled downward by this accelerating gravitational force. Combine a steady horizontal forward line with an accelerating vertical drop, and mathematically, the result is always this perfect parabolic arc.
Section 4. Velocity and momentum.
Let's dig a little deeper here. What's actually happening to the energy, the speed, and the momentum as our lion, or our bullet, flies through this parabolic path? Well, at any specific microsecond during the flight, an object has what we call instantaneous velocity. This velocity is always pointed right along the tangent of the curve. And remember our golden rule. This instantaneous velocity is just a combination of its constant horizontal speed and its ever-changing vertical speed.
This creates some pretty wild shifts in energy as the projectile flies. As the object climbs to its maximum height, it slows down because gravity is literally fighting it. So its overall speed, its momentum, and its kinetic energy drop to, well, their absolute minimum right at the peak of the arc. But, and here's the crazy part, they never hit zero. Why? Because even at the very top, when vertical motion pauses for a tiny millisecond before falling back down, that horizontal motion is still aggressively pushing it forward.
Section 5. Time, height, and range. Now, to figure out exactly where our projectile is going to land, how high it will go, and how long it'll hang in the air, we don't need to get bogged down in massive textbook equations. We can just neatly organize the mechanics into the big three variables: time of flight, maximum height, and horizontal range. The beauty of this is that all three of these outcomes are dictated entirely by just two inputs from you: how fast you launch the object and the angle you launch it at. Notice how the height and the time depend heavily on the vertical component, while the total range needs a perfect balance of both your speed and your angle.
And speaking of angles, there's this amazing mathematical quirk noted in the source text: complementary angles. If you launch a projectile at 30 degrees and then you launch another at 60 degrees with the exact same speed, you know what happens? They literally land in the exact same spot. The 60-degree launch will fly way higher and stay in the air a lot longer, while the 30-degree launch will be this fast, flat line. But their total horizontal distance, their range, will be exactly identical.
Pretty cool, right?
Section 6. Mastering the perfect angle. So what if you just want to absolutely maximize your distance? What is the ultimate secret angle?
The absolute perfect angle to achieve the maximum horizontal range is exactly 45 degrees. Not 44, not 46. Exactly 45 degrees. At that specific angle, you are perfectly balancing the amount of time the object spends in the air with the horizontal speed that's moving it forward.
And this isn't just a chalkboard theory. This is literally the holy grail of sports. Whether you're a track and field long jumper trying to set a world record, a cricketer trying to hurl a ball a massive 100 meters from the boundary, or a footballer taking a goal kick for maximum distance, hitting your launch at exactly 45 degrees is your mathematical ticket to success.
Now, I want to leave you with a final thought, pulling from a really interesting problem highlighted in our text. Everything we've discussed today, the perfect parabolas, the constant horizontal speed, that flawless 45-degree angle, it all assumes we are operating in a perfect vacuum with zero air resistance. But what actually happens in the real world when the air fights back?
The text actually runs the numbers on this. Just a tiny bit of air friction, an opposing force slowing you down by just 1/10 of the force of gravity, shaves a full 9% off your total time of flight. That 9% might not sound massive, but it completely alters your trajectory, shortens your distance, and could honestly turn a perfectly calculated circus stunt into a complete catastrophe. Which really makes you wonder, if just a tiny bit of air resistance changes the math this drastically, what other invisible forces are secretly dictating the physics of the world around you every single day?